Well, thanks very much. As you can probably tell in my last lecture, I was already feeling a bit sick, so I wasn't making a lot of sense there. And I'm still a bit sick, so fair warning to the front row or so. Okay, so thanks again to Blair for stepping into the frame. Yeah, extraordinarily nice of her. Let's pick up where we were. So what was I going on about last time? What was I waffling about? We were talking about the completeness of ACVF. Let's call it P, Q for suitable pairs PQ. And I gave a kind of sketch proof of that. And Bjorn reminded me afterwards that I misspoke on one point. What I meant to say is that once we've done this business of taking this friend here, this subfield, and then we think about what's left inside our big field K. Let's take some little element X. What I said at some point is that the linear type of X over henselianization of this already is enough. That's not quite true, and I'm sorry about that. What I meant to say is the important intermediate step is the relative algebraic closure, which, since we're in the ACVF setting, is actually algebraically closed. So that's the algebraic closure. Over this field, the linear type of X is enough to determine its L-val isomorphism type. And the crucial extra part of the argument is that, of course, since I may as well say this is Henselian, or, well, even without that, the point is this thing is uniquely determined up to isomorphism over the tensor product. So that was just a small correction to last time. Okay. I also have a little small puzzle on the theme of on the theme of something we spoke about before, which is take a proper elementary extension Q star of Q. Let O be the convex hull according to the usual ordering, and check that makes sense to you, the usual ordering. Take the convex hull of Q and verify that O is a valuation ring. And then I'm asking you, what is the theory of the residue field? It's a little puzzle. All right. So I want to kind of move forward and talk about several next steps. And that is Henselian valued fields of equal characteristic 0 more interestingly, algebraically maximal Komplansky fields. And then tomorrow, I'll get to talking about tame valued fields and towards tame perfectoid fields. But just kind of hinting at that a little bit. I'm not going to get really deep into that topic. Jahnke and Kartas. Okay. So, kind of continuing here, heading towards thinking about Henselian valued fields of equal characteristic 0, let me just give another couple of examples. So just take K, any field of characteristic 0, and gamma, any ordered abelian group, and I just wanted to at least once write out what this thing is. This doesn't have to be for the definition of characteristic 0, but for what I'll then say is a characteristic 0. So this is going to just be the set of formal sums. Maybe let's call it a gamma t gamma, gamma running through gamma. There is a constraint, the support, which is the set of gammas, little gammas, where a gamma is non-zero, is well ordered. All the A gammas, of course, come from the residue field, and that's it. So this generalization of the usual kind of power series field is called something like a Hahn series field, or a generalized power series field. And we'll see, right, I mean, one can check that these are all maximal.
You don't read t to the power gamma as a one formal symbol, or?
Yeah, this is, I mean, I'm just sort of writing some notation at this point. But it's also true that the set of elements of the form t to the gamma form a multiplicative subgroup isomorphic to gamma, capital gamma.
So if you multiply t to the gamma times t to the gamma 2 is gamma 1 plus gamma 2.
Yeah, what you're asking is what's the arithmetic on this field, and it's what you expect. Which means when you multiply, you add in the indices. When you add, you just add.
Yeah.
These are maximal, which means no proper immediate extension. That's a remark relevant for characteristic. P, perhaps just for our purposes, certainly therefore they're Henselian. And if, well, that's it's a fact that something like this is already an algebraically closed valued field with respect to the t-adic valuation. I didn't tell you what that is yet, so let me do that now. What's the t-adic valuation? Well, you already know what the t-adic valuation is on C double brackets t, so it's sort of the same thing. You just ask yourself, what's the minimum of the support of this element? Right? And if the element was 0, then you just write infinity. So this family of valued fields gives a very, very flexible way of creating examples. Let me give another example, which is sort of due to, I mean, it's due to anyone really, but these are called the Newton-Poisson series. I tend to write it something like this, just as a symbol. What do I mean? I mean the direct limit of these things. Okay. And then it's a theorem that in characteristic 0, well, let me write it like this. Let me just say C Poisson series is a model of ACDF. 0, 0. That's a theorem. I mean, one needs to check that. If you want, you can attribute that to Newton. All right. So, it's not very. I'm sure that's anachronistic. Okay. It's funny too. Okay, so let me just now give a definition, which is, let's say, let capital H be the L-val theory of Henselian valued fields. H00, that's just H plus equal characteristic 0. What's our goal? What's the statement we're going for? Let me just write it as a statement. Theorem. The AKE theorem, if you like. Version 1. Let K be any field of characteristic 0. Let gamma be any ordered abelian group. Then, the theory H00 plus axioms that say my residue field has the same logical theory as K, plus axioms that say my value group has the same ordered abelian group theory as gamma, this theory is complete. So specifying that you're in the background setting of Henselian equal characteristic 0, plus fixing any specific residue theory and any specific gamma is enough to just tell you everything about the L-val theory of Henselian valued field of equal characteristic 0. Yeah.
How do you have axioms that are saying that your theories are equivalent? It seems like you're quantifying now over first order statements?
Yeah, that's a really great question. Let's not get too formal about this, but how about the following? Let me just reminder that in L-val, the way I set it up, we have three sorts, three types of variable symbols, and in the first sort you have the ring language that lives on the main field somehow. It lives on the main field, and then you have the sort for the group, and so on and so on. So let me do this as an example. Right, suppose that we're interested in the case that K is R. What's one true statement about R? Consider, for every x, there exists a y such that x equals y squared, or minus x equals y squared. How do I say a true statement? Right, we all agree with that statement. Okay, so if my residue theory that I'm targeting is the theory of R, which we already discussed a few times, how do I force in the theory of a valued field that its residue field should have that theory? Well, let's call that phi. Then I could make a new iota phi, iota for interpret, for example. Just how do I interpret some statement about a field, but interpreting it on a residue field? How do I say that? Well, I would say for all x in that residue sort, right, I'm allowed to specify which sort my variables come from. There exists a y in the residue sort such that x equals y squared. But here I'm being cheeky, right? Because I'm using square like it's a symbol in the ring language. It's not. That's just a code for saying y times y, but that times ought to be from the times symbol in the residue language. So that's in the residue sort. That's the times symbol in the residue sort. Right? That's just or. That's the minus symbol in the residue sort. That's the you get the gist now. Okay? So you just rewrite every sentence in the theory of K, little k, as a statement about the residue sort.
Okay, so the theory of K is external to all of this, and we're just like taking all the theory of K.
If you want to think of it as a sort of procedural thing, yeah, imagine you're given somehow a list Okay, since one of the themes of this is computability, I'll say something about that in a second. Yeah? All right, in that case, let's hold that thought. If you already see where I'm going with it. Okay, so that's the theorem. So, consequence, let's just have an immediate example. I already told you that Newton knew something about valued fields, but he probably knew this too, which is, take any, z plus pi z as an ordered abelian group. This thing is elementarily equivalent to, I don't know, Q, just somehow adjoin symbols clumsily doing the same sort of thing, and then take a Henselization. These are different fields, but elementarily equivalent. One example. Or how about, I don't want to give the, okay, I'm going to give the game away a little bit, but R star with this valuation ring coming from the with this valuation ring coming from the convex hull of Q, that's just the same as taking sort of R double brackets Q, something like that. Sorry, I'm writing it as though it's a here I meant to write the notation T to the power. Now, why is that? Well, you should go away and think about this a little bit. If you have some elementary extension R squared, right, it's a nice exercise there's a lot of nice exercises in sort of the more basic parts of the model theory of real closed fields to see that also the residue fields of these kinds of valuations that come from convex subrings are also real closed, and such valuations are Henselian, and they have divisible value groups. You can check all of that, and that's what's going on here. We've got a real closed residue field, and we've got a divisible value group.
Sylvie, you didn't specify the valuation ring on the right side.
No, I didn't, but the theoretic one. Yeah. I'm just specifying it here because I haven't sort of been too clear about this kind of example before. But if I write a power series field or a Hahn series field, I'm going to mean the theoretic one. So I quite like these examples because it's completely unobvious why these should have the same elementary theory. But the theorem tells us. Let's do a more interesting example now, right away. Perhaps in some ways the most classic example. Let U be an ultrafilter on the set of primes and consider the following. Both of these are, what are these things? We already talked about ultraproduct of the QPs as valued fields with respect to this ultrafilter. Ultraproduct of the FP double brackets T is just some power series in positive characteristic. These are our favourite local fields. What do we know about these things? Well, for example, the following. They're both Henselian. Why? Well, each QP is Henselian, and we already know by Walsh's theorem how individual sentences that are true in every factor, or even in like most factors, go up to the ultraproduct. So each of those infinitely many Henselian axioms are true in this ultraproduct. More basic things too, right? It's a valued field. What's the characteristic? Now we need to be a bit careful. Non-principal. So it's not one of those trivial ones we talked about, you know, just I'm a set that contains 2. That's a pretty boring one. That sort of focuses everything on the number 2. But if it's non-principal, then this will not have residue characteristic 2. This will not have residue characteristic 3. This will not have residue characteristic, pick your favourite prime. And every remark I've just made about this is also true about this. Let's now ask ourselves the final question, what about the value group? Well, here we've got a Z group, something elementarily equivalent to Z. Here we've got a Z group, something elementarily equivalent to Z. Even the same group, actually. Right? But I'm trying not to emphasize that part of the story. And so we now know this. In particular, and I won't get into this, this allows an asymptotic or sort of almost everywhere solution to Artin's conjecture. It's the original kind of punchline of these papers for QP. Okay, now I will say more about the proof, of course, though I already showed you the proof actually, because it's the same proof as for ACVF 00 with one extra ingredient. But let me tell you a sort of more high-tech version of this statement over here on the left. All right, so a more high-tech version might say the following. Well, you would take a lemma like this. Let K1, K2 be the models of Henselian valued fields of equal characteristic 0. So they're both Henselian valued fields of equal characteristic 0, both extending some K, some common subvalued field K, such that the first value group extension, so the valuation, the value group of K1 over the value group of K is torsion free. And actually it's not terribly important this point, but let me make it anyway. This extension here, the residue field extension, do you know what, I'm not going to say that because that's actually a redundant hypothesis, I'm sorry. Hang on, how do I want to say this? All right, let me put it like this. Such that this is torsion free and the residue field extension is relatively algebraically closed. Okay. Given some maps between the value groups of the, as it were, the left-hand side K1 into the value group of K2 over the common subgroup and some other map doing the same thing for the residue fields, so given these two sort of pilot maps that send across the value group and send across the residue field, and supposing K2 is sufficiently saturated, I'm putting that in inverted commas because I want you to ignore it, we get an L-val embedding K1 into K2 over their common substructure, which induces these two sort of pilot maps. Now, I haven't told you what sufficiently saturated is, but what it really means is there exists some elementary extension of K2, which if I then replace K2 by that, it all works. So, up to this kind of blowing up to a slightly bigger but logically equivalent extension. So this is a sort of algebraic feeling embeddings theoretic version of this. The link between the two is not obvious right now. This is a statement that says, in the context of henselian equal characteristic 0, the theory of the value group, the theory of the residue field is enough to fix the full theory. This says embeddings of value groups, embeddings of residue fields lift to a common embedding of valued fields. What's the link between the two? I'll answer that now. Do some board cleaning. Now's a good time to ask a question. Anyone solve the puzzle?
We had no time to think about the puzzle.
That's a very fair point. Didn't I set a puzzle the other day as well?
Well, but that there was also not really time.
How about this? How about convince me, or convince yourselves, that the residue field of Q star with respect to that valuation ring I just spoke about has a square root for 2. The square root of 2.
Excuse me, can I make a random guess?
Sorry?
Can I make a random guess?
Can you make a random guess, please? Please do.
I guess real close field.
It's real close fields. 10 points. Was that obvious to you before I said about square root of 2?
And that's a hint.
That was a hint indeed. Okay, so what's the link between this sort of embedding lemma and the AKE theorem? Well, the embedding lemma that I just mentioned is a sort of standard ingredient for these kinds of completeness arguments. Now that's or relative completeness. Sorry?
Can you move the backboard up?
Yes, I do. That's a very good one. No, I think the answer's no, actually. I can't move the backboard. How do I do that now? Okay, 2 seconds. Okay. So, how do you go from an embedding lemma to a kind of completeness or relative completeness? Relative because it's all about fixing your residue and value group theories. That's some standard part of model theory called a back and forth argument. And I don't know if that got mentioned in one of the talks I was a bit too sick to come to, but a standard back and forth argument. Let me just draw a picture. Right. Suppose you start with K1, you've got K2, you've got K down here. Right. Suppose you knew already that your 2 value group theories on each side were as close as possible, were as close as possible, that every embedding could always be extended to an isomorphism, or maybe even they're just isomorphic. And suppose the same for the residue theory. So I'm just saying, suppose we always have these pilot maps whenever we want them. Well, the embedding lemma kind of gives us something a bit like that, but maybe we have to sort of go to this elementary extension, K star, to get that I mentioned. Right? And then there'll be an image in here. There'll be some sort of phi of K1. So what? Well, that's across this isomorphism, because an embedding is just an isomorphism, it's less precise about it, it's codomain. Across this isomorphism, we have this thing has a common subfield with this thing. So that means, assuming all these pilot maps exist whenever you want them to, you can go backwards, but perhaps at the cost of going to another elementary extension. And again, there'll be an image over here of this thing. And now you see what happens. It's a ladder. It just goes like this. Okay? And being a bit more careful about that, you get in the end sort of interwoven direct limits, and that's a way of showing, subject to suitable hypotheses that this kind of embedding lemma always just gives you relative completeness. So what I'm trying to say is the entire proof reduces to embedding lemmas. Okay. So how do we do this embedding lemma? Well, as with ACDF, it's a structural, it's first and foremost a structural argument. Right? It's always about describing the structure of something. So let's just take K1 some henselian valued field equal characteristic 0. And I just want to understand, to what extent does its structure depend on its value group and residue field? That's it. To what extent does its structure depend on its value group and residue field? Well, I already told you that you always have a maximal subfield on which the valuation is trivial. In fact, in general, you'll have plenty. But you'll always have at least one. So you'll always have one of those residue map sections that I mentioned, some little k. If you like, you can think of it as an embedded copy of the residue field, suitably embedded, or just as a subfield. I don't really care much. Now, it's not necessarily true that we'll always have a cross-section. That's okay, because I don't mind going to an elementary extension and telling you about the structure of that thing. So, without loss of generality, because I don't mind going to an elementary extension, there exists a cross-section. Meaning a cross-section of the valuation map. And I prefer to write that as t to the gamma. Now that's just a set, it's a multiplicative subgroup, so I can think of, you know, the subfield generated by it. Right. And now I can think of these two things as some sort of disjoint extensions over Q in the suitable sense. And what's the suitable sense? It's valuation disjointness. I believe is Franz Richter's notion. So here we have some sort of very canonical tensor product. Again, same argument. Now I need to tell you what goes on in the relative algebraic closure. So let's say I want to look at the relative algebraic closure of this tensor product inside K1. I want to describe this to you in just a second, but let me briefly say that this part is relatively algebraically closed, immediate, and essentially, as before, this Kaplanskian theory of linear types, pseudo-Cauchy sequences or approximation types, whatever you like to say, linear types are enough. And that tells us, as before, that this is an existentially closed extension. I did say what that was last time, but it's a bit technical and logical. Let me just say that every equation, meant in the sense of any inequality using valuations or any polynomial equation, anything like that, also Boolean combinations of those things, any equation defined over this subfield that has a solution here already has a solution here. And that's exactly the same argument when working over this relative algebraic closure, it's exactly the same argument as in the ACVF case. The slight difference is between these two, because in the ACVF case, there could be, for example, in equal characteristic P, there could be a big difference between the Henselization of this step and the relative algebraic closure here, but it didn't matter because it's sort of canonical. It's just going to the algebraic closure. In other words, there's a unique up to isomorphism maximal immediate algebraic extension. That's if you already know those words. Since we're in equal characteristic 0, there's no defect. Which means this already equals the Henselization of that. That's the magic. Because in fact this part's already immediate. Because I've put all the residue field here, all the value group here, so there's nothing left to do in terms of value group and residue field extensions. So even by the time we get to the tensor product, everything else is immediate over that. So now it's just about the structure of immediate extensions in equal characteristic 0, which are basically always nice. So that's kind of my picture that I like to draw for this argument. What's that got? That's a structural statement. What's that got to do with embedding learners? Well, now we have the similar diagram for K2. Somehow all of these steps go across nicely now. Right? We're given this pilot map. Rho was which one? It was the value group one. Right? So I can lift rho. So that's rho gamma. Can I call it gamma 1 now? I'm going to put a lot of 1s everywhere. 1, 1, 1, 1, 1. That's on the one side. And that lives inside Q, T, gamma 2, you see? That's rho. Well, that's a lift of rho, really. Right, and there's something similar happening in sigma. Right, we get K1 sigma lifted inside K2. And you see how this goes now. Everything pushes across. Each step pushes across. Product, thingy there. Henselization, everything else is immediate. A posteriori, we actually didn't need to worry about this step. A posteriori, this is in fact an elementary equivalence, elementary extension, so somehow we didn't even need to embed this. But I think we only really know that after the fact. We only know that after having proved really AKE principles in equal characteristic 0. So I hope this argument made sense to you. Each step lifts, basically. And just remember that this without loss of generality step required me to pass to an elementary extension of K2, of both sides, because I needed to get that cross section. Okay, that's kind of my personal preferred take on this argument. I think it's quite similar to the one, or more or less the same as the one presented in Prestel and Dalzell, that book. But there are many other arguments for this kind of theorem and how to produce these embeddings. I'll invite you to look those up. There are many more consequences of this embedding argument than just the AKE theorem in that form, let me now outline them. But before I do that, any questions about this part? Let me put it this way. I see each sufficiently saturated Henselian valued field of equal characteristic 0 as being built naturally from three things. Residue section, value section, some immediate, nice immediate stuff. Transcendental type in the language of Kochen. All right. Let me now just say that the immediate corollary is the theorem, as above, but also that the class of models of Henselian valued fields of equal characteristic 0 are an AKE square class for all the squares that we discussed before. So that's elementary equivalence, that's exactly that statement there. Existential equivalence, elementary substructure, existentially closed substructure. These are just variants on a theme, keeping track of slightly different consequences of this standard embedding argument. Plenty of remarks. Right. This is all resplendent. What does that mean? We could work with richer structures than just residue fields and value groups. We could do all of these arguments with respect to some, make your choice, some difference algebra, some, I don't know what, some sort of colouring on the ordered abelian groups. We'll then get an Kochen Ershov principle about the theory of that kind of residue field, the theory of that kind of ordered abelian group in those richer languages. But you can't magically get something that allows extra rich structure on the main valued field itself without doing more work, of course. So extra structure on residue fields and value groups is allowed. In fragments, these are just a few small remarks that are not as interesting as the main result, which is to say we could even generalize to, I could replace these symbols by equivalent or something like this, etc., where F is just a thing like E, A, E, blah, 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 A, whatever formulas. If you fix your complexity, in various senses, you get the same kind of transfer statements. So if you wanted to say, what does Kochen Ershov theory tell me about the EAEA, meaning the EAEA theory, meaning the set of sentences that are true in a valued field, which, at least up to logical equivalence, can be written as some existential quantifiers, then some universal ones, then some existential ones, then some universal ones, then something quantifier free. Well, this precisely tells you that the EAEA theory is determined by the EAEA theory of value group and residue field. And we get this computable elimination This is what I called before the standard consequence. It's one of the standard consequences. Where we get, there exists a computable function, epsilon, from all sentences in the language of valued fields. I could do this in a richer language as long as the richness is constrained to the value group or residue field. going to what? Boolean combinations of sentences from the residue field language and sentences from the value group language, the Archimedean group language. It doesn't matter. It could be, it's actually, you can say positive Boolean combinations. It doesn't really matter. Such that the theory of Henselian valued fields of equal characteristic 0 always believes that phi is equivalent to its limit. So every statement you want to make about a Henselian valued field of equal characteristic 0 can be computably translated into a statement about residue fields and value groups. And this also works resplendently for suitable computable languages, and it works in fragments for suitable computable fragments. But not all fragments are nice ones like that. I'm saying the word suitable a lot because there are plenty of technical hypotheses one needs to write down, but the key idea is that this is a very rich theory now. When did we start actually? I think we were a couple of minutes late, but can you remind me, Jane?
Yeah, I would say like 15 minutes.
15 minutes left. All right, marvellous. Okay, questions? Now's a good time for questions.
So do you have a plus in front of the boolean? Like...
Yeah, I just mean, I'm just trying to say disjunctions, conjunctions, statements of those. Now that's not a very interesting strengthening for a couple of reasons. One, that you can always push negations through by De Morgan's law. Well, maybe that's the main reason. So what's another consequence, another kind of remark on these lines, is that the subspaces of the class of all Henselian valued fields of equal characteristic 0 that you can pick out with an axiom. Let me just, I'll draw the picture. It's a nice picture.
Excuse me? Is that kind of principle works for universal expansions of?
Say that once more, this was making too much noise. Say again?
You said this kind of principle works for universal expansions of the residue field and the group.
Yes.
Say, for example, for ordered fields, does this kind of principle work?
Residue field, yeah, it can be ordered.
But the whole group cannot. I'm sorry, but the whole field.
Well, then you need a different embedding limit to make sure that you're preserving things like that. There is a theory of real closed valued fields, for example. But it's important to say that when I use the word like resplendent, what that's saying is the pilot objects, the little objects that we're trying to eliminate down to, these can be richer, right? Somehow on their own. But we don't magically get extra structure on the big valued field. Essentially, it's you can't get something for nothing kind of statement, right? With the same embeddings, we're not taking care of anything else. I haven't told you how to take care of extra structure on the valued field. So it's just not plausible that the same argument without refinement could give you something more. However, it was a fairly, I didn't need to know anything particular about these embeddings between value groups and residue fields, did I? So if those embeddings happen to be, order preserving or difference operator preserving or whatever it was, whatever the extra structure was, if we were working in that category, well then fine, then the final thing we construct still gets constructed and it still induces those maps. That's the essence of it. Okay. So I'm giving you kind of a list of remarks, right? The kind of extra bonus material. Like in the old days. We had those DVDs. Standard consequence. I'm still going with these standard consequences. So let F be any theory of fields. Again, it could be a theory richer than that, but I don't want to kind of overwhelm this conversation. So take two theories, one of residue fields, it's a theory of fields, and a theory of ordered abelian groups. Then the theory I am Henselian equal characteristic 0. Can I write some notation at the same time? Together with residue field models F, together with value group models, sorry, I don't know why I wrote it like that, models G. This is the kind of thing I was talking about before, where you stick some statement about residue fields into the language of the valued field, just by saying all the symbols I'm talking about should be symbols from the residue field or value group. Turing equivalent, decidability theoretically equivalent, could also write here many 1, but then I need to do something different on the right-hand side. So let me just indicate that one can make a statement slightly stronger. So let me just write this. So what does this mean? This is the Turing sum. So this is some sort of code for pairs here. And I really mean here like the deductive closure of F and the deductive closure of G. And I mean the deductive closure of this theory. So what I'm saying is the decidability problem for this kind of theory is, from a Turing equivalence point of view, exactly the sum of the decidability problem on this theory and the decidability problem on this theory. It's neither more nor less, it's equivalent. And that's just a straightforward consequence of this computable elimination business. The key observation here being that these don't need to be complete theories. Otherwise I haven't said, well, let me just, in particular, right, the theory of this as a valued field, and again, characteristic 0, is Turing equivalent to the theory of K, Turing sum, the theory of gamma. So the decidability problem for the valued field is the sum of the decidability problems here. And this also works fragment by fragment. And it also works resplendently, subject to working with computable languages on the valued field nesting group. So there are lots of these sort of enrichments of this family of embedding principles and AKB principles available to us. So I've told you now a few statements that are about computability. Let me now tell you one that's about definability. Theorem, theorem of pass. If we work in a language, LAC, which is the language of valued fields, but I want to enrich it by a symbol going from the big field to the little fields, multiplicative groups, and that will always be interpreted in the models I'm talking about by an angular component. So in telling you what the language is, I'm also saying that I want to work in a theory that specifies that this symbol ought to behave like. The theory of Henselian value fields of equal characteristic 0 admits that, suitably adapted for this language, so maybe I should write AC, admits a quantifier elimination relative to the value group and residue field. Now, that's a bit of a delicate notion, this relative QE. That means one of two things. Let me tell you the slightly stronger thing. It means that every formula now allowing variables, every statement about n elements from this language is actually equivalent to some sort of Boolean combination of quantifier-free statements about those same variables in this language, together with formulas living in the residue field sort, composed with suitable terms to get you there, and the same thing for the value group. So I could write this a little more precisely, but I think for fun I won't. So what does this tell us? This tells us, corollary, but maybe it's even easier than that, every infinite definable subset of a Henselian value field of equal characteristic 0, and I mean every infinite definable subset of K of the main field, meaning I'm not interested in subsets of the value group, subsets of the residue field. How would I say now? Sorry. Subset of K. Non-empty interior. And that's because essentially nearby to any x living in K, nearby there, the same quantifier-free information about x, any x prime that's sufficiently close has exactly the same quantifier-free LAC type as x itself. Yes?
So given the types of, or given the sorts that we have, how do we define a function from K, and specifically exclude 0?
You mean that?
Yeah.
Well, I'm not, I take your point. I take your point. That's always the question when you have things a bit like this. Like, someone asked me the other day, why are we working in the language of rings, not the language of fields? And I think there's probably many answers to that, but one is about complexity.
Oh no, I'm just talking about.
Let me take a different tack. In order to say what this means carefully, of course, you really, to be formal about it, need to say what this should do on 0.
Okay.
But then we also need to know that it didn't matter what we said.
Yes, okay.
Right, so if we just say, well, by this, what Sylvie means is AC of 0 is 0, okay. And if you look at the non-zero things, then
that makes more
something
sense.
like this. But then you run into the question of, well, what about this? Why did I do that? And technically you need to sort of, I suppose, check that any sensible choice you made was as good as any other.
Okay, that's right. Okay. So you just ignore 0 by saying it has some value, and that one doesn't matter for what we're doing.
Yeah. Okay. So let me move on. Let me just make the remark. This does all go wrong. In positive residue characteristic. I mean, certainly in equal positive characteristic, but also in positive residue characteristic, in full generality, we don't get this kind of strong theory. Different aspects of it certainly break down. Excuse me. By the way, I didn't say anything about how one proves this kind of thing. Essentially, one needs to do an embedding argument, just like we were doing before, but work over just some sort of subring, some valued subring. And one needs to just, essentially the only difference is you need to argue, which works because of the AC map, that first step to get to a submodel, we can already make an isomorphism at that level, or an embedding at that level. And then once you've done that, then you're in the setting of an embedding problem over a nice substructure, perhaps a model or whatever, and then it's the same argument after that. Okay. Let me now talk about, which I think is my section 3, which is about Flamsteed's hypothesis. Okay, and I'm just going to simply say give a couple of definitions, and then I'll finish this next time. A valued field KV, I'm now being clear about the valuation for some reason, is separably, but I want to make several definitions in one go, so separably, algebraically, but I want to make several definitions in one go, maximal, if it admits no proper separable algebraic extensions, which are immediate. No proper immediate separable algebraic extensions. Okay. Now, clearly, from the way I explained this embedding principle, the fact that at this point here we could jump up to a very nice submodel, in fact, and we could do that in a canonical way, that was key to the argument. That was absolutely key to the argument. It's also true in this setting, it's even the Henselization here, but if we could do this step, and it was, somehow canonical enough, you moved up to isomorphism, and supposing that the thing you ended up with was algebraically maximal, then the whole argument would go through. If you always have that flexibility, if you always have the flexibility to, once you're in the immediate bit of the problem, know that you can go to to a maximal immediate algebraic extension and do that in a canonical way, then you're good to go. That's my assertion. Because that's all we used here. We used that once we got to this point, we could then push across that embedding, and the canonical thing, the fact that there was one of it up to isomorphism, that was really enough. I mean, that's enough to get that the embedding goes across. And then the fact that the linear types suffice as before is because you're essentially because you're in an algebraically maximal model here. So my assertion is, if that part of the argument could be done like that in some embedding problem, it would always work. So knowing when you've got these things and they're canonical is key. And I think I'm out of time, so maybe I'll be giving one more talk tomorrow. So I'll leave you on that cliffhanger. Thank you.